Right. So it's my pleasure to introduce. My goodness. What have I done?
Fluid mechanics.
Friction.
A pleasure to introduce Pierre Haas as our speaker today. So Pierre has been in Cambridge for now how many years?
This
8
is
years.
the ninth year, yes.
Ninth year. He was an undergraduate here in mathematics. He did a PhD here with Ray Goldstein that he finished, what, a year and a half ago?
More like a year ago.
Okay, a year ago. And he just won a big prize from the APS for the best thesis in biological physics in the entire world. That's him. And he's now a junior research fellow. He switched college. He's now at Modeling College, so he's going to be here for another, 3 years or so. And his thesis was on problems which are very close in spirit to our workshop, because he's going to tell us a lot of problems on shapes and how to change shapes.
Thank you very much for the invitation and for the introduction. I'm going to talk about a problem in developmental biology that we've worked on for a number of years now. This started with experimental work done by Stephanie Hoon and Aurelia Hohnekamp-Smith. Julius Kierkegaard took the part of the Python wizard who converted the experimental data into something a theorist, moi, could work on. And of course, Regolchen has been the alpha and the omega of all of this, and general purveyor of scientific wisdom. My work was at some stage funded by the FSSC under a studentship and then a Dr. Prize Fellowship, and is now, as Eric already mentioned, funded by a research fellowship from Magdalen College. Say what you will about Oxbridge colleges, but their shields are generally more aesthetically pleasing than the logos of the research agencies. The first paper dealing with developmental biology might be this work by Robert Boyle in the first ever volume of the Philosophical Transactions of the Royal Society in 1665, an account of a very odd, monstrous calf. Now, of course, over the course of the ensuing centuries, biologists have realized in order to study these problems of developmental biology, one should really understand a number of very stereotypical processes that happen in very many organisms. One of these might be gastrulation, the transition from a spherical ball of cells to something with a topology of a torus, which therefore looks more like an adult human being with a mouth and a digestive system. Louis Wolpert therefore said that it is not birth, marriage, or death, but gastrulation, which is truly the most important time in your life. However, in very many of these problems, in very many of these systems in higher organisms, these deformations of cell sheets arise from a rather intricate interplay of cell shape changes, cell migration, cell intercalation, and cell division. And so, if we want to get a more mechanical understanding of these processes, we should probably look at even simpler systems. So the first part of my talk will deal with the mechanics of this cell sheet folding in a green alga called Volvox. Volvox actually appears on the frontispiece of this weird and wonderful book by Julian Huxley, The Individual in the Animal Kingdom, in which he says that in some colony like Volvox, there once lay hidden the secret of the body and mind of man. It was a day and age when one could use different language in scientific papers. And I hope to convince in this talk that in some alga like Volvox, there once lay hidden the secret of the mechanics of the formation of the body of man. So here's Volvox in a family of green algae called the Volvocales, starting with organisms such as Gonium, consisting of 8 or 16 cells in planar arrangement. Each of these cells has 2 flagella, and the coordinate beating of these flagella makes the alga swim. As the cell number increases, the organism become spherical, and then undergo so-called germ cell differentiation into 2 cell types: somatic cells with 2 flagella on the surface, and germ cells, Orgonidia, on the inside. These will then divide and give rise to the embryos of the next generation. For this reason, Volvox has become a model organism for the study of multicellularity, because it features this very prototypical transition from a single cell type to multiple cell types. If you now zoom in onto one of these Volvox spheres, what you see is this surface of parental somatic cells with flagella. These cells are connected to each other by cytoplasmic bridges, thin membrane tubes that result from incomplete cell division. The gonidia have divided into embryos which are confined to fluid-filled embryonic vesicles, and the whole organism is otherwise held together by a gelatinous extracellular matrix.
This is a very complex diagram. Would you explain a little bit what the life cycle of the...
So the life cycle of this alga, well, that
Oh.
is this organism. So after hatching, as it were, these germ cells start to divide, the whole thing grows, and then they hatch out of the thing. However, just after the division of the germ cells, there is this strange process of inversion where this alga literally turns itself inside out. Imagine taking your socks off and turning them inside out. And they must do that because at this stage, the ends of the cells whence will emanate the flagella point into the sphere. And so in order to eventually be able to swim, they must turn themselves inside out. So here's a visualization using light microscopy of an Volvox spheroid with the embryos inside. And I now managed to play this video. If I have a cursor, yes. You can indeed visualize this inversion. Notice that this is sped up, so the whole inversion lasts about an hour, so this is really a very, very slow process of development.
So this is an open sphere, or is there some it's some?
You start from a single cell, which divides into this spherical thing. And so there's sort of some cells that are next to each other, but which are not connected to each other. So that defines the whole, which they can turn themselves inside out. And actually, this inversion can happen, depending on the species, in one of two different ways. In so-called type A inversion, 4 lips open at the anterior pole of the shell and peel back to achieve inversion. I'm mostly going to focus on type B inversion, which starts with the circular invagination at the equator. This enables the posterior hemisphere to invert, and then the thialopore, this opening at the top, can widen and peel back to achieve inversion. So this type B inversion in particular shares features such as invagination with developmental events in higher organisms. At the cell level, this type B inversion arises from a rather complicated process of different types of cell shape changes happening in different parts of the cell sheet. But the crucial cell shape change that drives this initial invagination is the formation of so-called wedge-shaped cells. Imagine having 2 cells next to each other initially, which then become thicker on this side and thinner on this side. At the same time, the cytoplasmic bridges, these cell-cell connections, can move to the thin wedge ends, and so the cells will splay, and therefore the cell sheet will bend.
Just one question. I thought that the cells were more distant from one another, or they were embedded in a matrix.
So that is in the adult Volvox. In the embryo, so this sort of enclosed, somewhat larger fluid-filled embryonic vesicle. So to describe this, I'm going to derive an elastic model, and I'm going to derive various versions of this elastic model at various stages of this talk. But just to start with the simplest version, we're going to start with an elastic shell of radius r, thickness h. It's characterized by its arc length s, and this is rho s from the axis of revolution. The deformation is axisymmetric and take arc length to capital S and distance from the axis of revolution to rs. This deformed geometry is characterized by stretches fs and phi in the meridional and circumferential directions that describe how a little patch of cell sheet deforms. They're also described by the curvatures of the shell, which can be described in terms of the tangent angle. Now, this shell might also have intrinsic values of these stretches and curvatures, that will in principle differ from the values in the deformed geometry, and which might also differ from the stretches and curvatures of the original spherical shell. So we can use these to construct elastic strains in these differences and curvature strains. The elastic energy for this kind of problem is the sum of two terms. There is a stretching term proportional to the small thickness of the cell sheet, and there is a bending term proportional to its thickness cubed. There are two material parameters. The elastic modulus E, which is an overall constant in this intrinsic description, and only ensures that the energy has units of energy, and Passos ratio, nu, which I'm going to take to be a half.
Sorry, rho is not a constant?
So rho is not the density, rho is the distance from the axis of
Yes, I
motion.
know.
So
I'm asking, is it a constant?
it's a function of arc length.
Then what's the difference between rho and r?
So rho was this distance in the undeformed configuration, and r was the difference in the deformed configuration.
Okay. Same coordinate.
Yes, it's a coordinate. There is one point that has to be kept in mind here, that if I give you a deformed shape, I cannot straightforwardly read off the intrinsic stretches and curvatures. In particular, the easiest way to see this is perhaps to take a sphere and homogeneously contract it by intrinsic stretches to a smaller sphere. In fact, no matter what kind of intrinsic curvatures I will then choose, I will always get the same sphere as the energy minimum. However, these might have non-zero or zero energies. Let's now get back to the problem of inversion. We saw that inversion starts when there are these wedge-shaped cells forming that bend the cell sheet. So in this setup, this would correspond to some sort of region with lambda, where the intrinsic curvature is negative of value, say, minus k. And if we then solve the equations numerically, we find these hourglass shapes, which do not agree with the mushroom shapes one sees in vivo. However, there are additional cell shape changes going on. For example, in the posterior hemisphere, the cells contract in the meridional direction, whereas they don't do this in the anterior hemisphere. So this really corresponds to having a reduced radius of the posterior hemisphere. If we add this into the model, we can indeed reproduce the mushroom shapes seen in vivo. In fact, we can play very many versions of that game. So here was the shape with just curvature without contraction. Here's the shape with contraction but no curvature. And again, we don't get the right shape. The combination of these two gives the right shape. But you see, there's also this region here, which has increased positive curvature. We might try to put this in as a region of increased positive intrinsic curvature, and again, we don't get the right shapes. We can sort of get the right shapes by, rather than reducing the radius of the posterior, increasing the radius of the anterior hemisphere. But that is not based on cell shape changes, and has to be discarded. If we now take this intrinsic curvature, increase it further, and widen the bend region, then we can indeed invaginate the shell. And so our first conclusion is that invagination results from a combination of active bending and active stretching. At this stage, I just want to take sort of a slightly different approach and think in some more detail about the mechanics of these different geometric modes of this active bending and this active contraction. The first scenario of active contraction really results from the matching of two different bits of shell of different radii, whereas the pure bending scenario results from the matching of different shells of the same radius but sort of disparate vertical positions. If you want to try to describe this asymptotically, you can try to solve for the tangent radius, tangent angle of the deformed shell as its undeformed value plus some small perturbations. In this asymptotic limit, these deviations are going to be localized to a small asymptotic inner region of width delta next to the matching point. Now, in this case of contraction, I want essentially displacements of size d over this distance delta, so I expect B to scale as d over delta. That is not going to work in the case where I only have bending, because there's net vertical displacement but no radial displacement. And so you need a lower order solution to be able to do the matching at next order. And so the correct scaling in that case is actually smaller, d over delta to 1/2, which corresponds to having large displacements for comparatively little upward displacements, which is exactly the origin of this of these hourglass shapes seen numerically. Larger deformation of this shell must be studied numerically, however. With the same setup as before, there's some width of some region of width lambda where the intrinsic curvature is negative of value minus k, and this results in deformations that move up the posterior pole by distance d. Now plot k against d. At small values of lambda, I am in this asymptotic regime just described. But as I then leave the asymptotic regime, these branches start to look more interesting, and in particular eventually become multi-valued as functions of k. So there must be a critical branch with a corresponding critical point that separates different kinds of behavior. At very large values of lambda, these branches become weird with loops and whatnot. But let's just focus on this region underneath the critical point, where locally the partial derivative of k with respect to d is negative. If you flip this diagram, it looks like the isotherms of classical van der Waals gas, and so what you have is this classical scenario of unstable and metastable solutions expanding underneath the critical point. You can put contraction to this picture by adding a reduced posterior radius as before, and what you generally observe is that as you decrease the posterior radius, i.e. as you increase the amount of contraction, the critical point moves to regions of lower critical curvature and wider critical width. What does this all mean for inversion? Well, clearly, contraction is an interesting geometrical thing. If you have two hemispheres that you need to fit one of them into the other, you should better contract one of them relative to the other. But actually, this shows that there's a mechanical role to contraction as well. Inversion starts somewhere over here in no critical curvature, no cell shape changes, and eventually moves to some region like so. But there are two possible scenarios. Either it moves around the critical point, or it eventually crosses this line of phase transition. So in some sense, contraction, by moving this critical point further down over here, facilitates a stable invagination. From a hypothesis testing-based approach, we don't see any sort of instabilities, any snap-through transitions in the system, so this means that this kind of consideration constrains the possible parameter paths of the system. You might be tempted to argue that, oh, well, you know, that all fits together, development should somehow be stable, but that might be teleology and one of Rudyard Kipling's just so stories. And I want to change gears slightly and talk about variability of cell sheet folding in Volvox. There's this lovely quote by Le Docteur Bichat, who in the year 8 of the French Revolution published his physiological researches into life and death, in which he said, translating somewhat loosely, if you try to describe animal function by calculations, you're a fool. I think what we've seen before, that might already show that this is not quite true. This is why I've chosen this rather unflattering painting of him. But then he goes on to say something very interesting. He says, the phenomena are always the same, and that is what matters to him. But their variations, for greater or for less, are without bound. I think this is a very general thing with developmental biology. The very vast majority of papers in developmental biology will implicitly average their observations and then derive some model, biological or theoretical, to describe these average observations. But actually this neglects all this information that is contained within within the variability of development. And so in this part of the talk, I want to hopefully provide some sort of proof of principle to show that this information can be usefully deployed. We need three things for this. First of all, we actually need to define what an average inversion sequence looks like. Second, we need a very much more detailed quantitative representation of this average sequence in terms of our model. And thirdly, we can then try to compare the exponential variability to the variability of perturbations of our average model and see whether we can learn something from them. Now, this is my token Darcy Thompson slide for this talk. Of course, the question of how to average biological phenomena was addressed by Dr. Thompson. In chapter 17 of the second edition, he shows how you can take fish of one species and by applying suitable stretchings and dilations, turn them into fish of another species. Now, in Volvox inversion, variability between shapes results either from different total sizes of the organisms. It can result from differences in the global timing of the progress of inversion in different embryos, or it can result from local differences of the stretching. Cell shape changes might not occur at exactly the same position in different embryos, and so there might be some relative stretching of shapes. If you put all these ingredients into some energy-based averaging approach, you can indeed derive an average inversion sequence, each term of which does look like a shape of an inverting Volvox. And you can even see that so the sequence of inversion, you now plot the time of an individual embryo during inversion against the mean time of all embryos. Each sequence seems to sort of proceed at constant speed, although some embryos seem to linger briefly in some stages during this development.
Sorry, what's different between different blue lines?
These are different embryos. So we have 22 embryo halves here that are averaged to give the right average sequence. Now, each point of these average shapes defines a covariance ellipse of the different embryos we've averaged. And so we can define the curves that are tangent to each of these covariance ellipses to give us some sort of standard deviation shapes, which are shown as these pink shadings, which you might or might not see on shapes. This shape variability results from a complicated interplay of A, the geometry of the averaging, and B, the changes in the underlying parameters between embryos. Now, some of this, what we're seeing here, is clearly geometrical. For example, if you think of having lots of embryo shapes and you're stacking them one onto each other, there might be some variability over here, and then as you go further towards let's say the anterior pole, this variability is going to sum these variabilities are going to sum, and so you get an increasing variability in the vertical direction as you go towards the anterior pole, which is indeed what you see in the embryos. But other features of these graphs are not geometrical. For example, look at these two regions over here. There's a larger variability in this region over here than in the immediately adjacent bend region, where the active cell shape changes that are driving this invagination, these wedge-shaped cells shape changes, are happening. So, with the eco of teleology pumping through the argument, you might say that is exactly what should happen. You should have a reduced variability in the important regions where the driving active cell shape changes occur. But again, that might be a just so story. So we should really think of this a bit more carefully, which is what I'm going to do after another elastic interlude. I have the same setup as before. I have an elastic spherical shell that's being deformed. Thinking of the differential geometry of this a bit more carefully, under the Kirchhoff hypothesis, which is this assumption that normals to the undeformed mid-surface remain normal in the deformed configuration, you can write down the metric of this surface as a function of the stretches, the curvatures, and the coordinate zeta across the thickness of the shell. Alain Gorilly has already given some talks in this program about the fundamental relation of morphoelasticity, saying that the deformation gradient that takes you from this undeformed configuration to this deformed shell is really the composition of, first, some intrinsic tensor that takes you from this configuration to some possibly incompatible intrinsic configuration, followed by an elastic deformation that takes you from this intrinsic configuration to the deformed shell. From the metric, we can write down this actual deformation gradient tensor, and we can actually also write down the intrinsic tensor by sticking some zeros onto the stretches to make them intrinsic. We can then compute the elastic deformation gradient, and for small elastic strains, but now arbitrary geometrical intrinsic strains, write down the strain tensor. There's one point which we make at this stage, which is this, that this theory is similar, but somewhat different from theories of non-Euclidean plates that are sometimes found in the literature. Because here we're describing an active biological material which is incompressible. So if I impose intrinsic stretches, then I have to also adapt the thickness of my cell sheet accordingly. For a doubly curved shell, so this intrinsic volume conservation requires solving a cubic equation which may or may not always have a solution. But anyway, you can now crank the handle and derive the energy. You can see that we sort of basically have the right definitions of the stretches and the curvature strains in our, so the strains and the curvature strains in our earlier model, but the energy actually was missing quite a number of terms that should appear. Now, if we take this model and impose general functional forms for the intrinsic stretches and the intrinsic curvatures based on the cell shape changes observed, we can indeed reproduce the experimental data. So in these graphs, the sort of pink shading line is the experimental average, and the black line is a curve predicted by the model. Of course, we can't really talk of fitting here, because I made this point earlier that I cannot, let me say that sentence again. Given the shape, I cannot straightforwardly infer what the intrinsic strains and curvature strains are, because they might be not unique. But we can certainly reproduce the shapes, and we can then, for example, infer what the meridional strains in these shapes are, which is not something you can just get by looking at the shapes. And yes,
is the agreement better than with the first model with the incomplete elastic energy?
We have never done the same sort of type of detailed fitting with this model. The qualitative finding we found is that we certainly, one of the main factors, you need lower intrinsic curvatures for invaginations with this model than for the previous one. And the intrinsic curvatures we have to apply here seem more in agreement with what you might get when you just look at sort of cell and roughly draw, imagine it becomes wedge shape, and what kind of curvature do you get. In fact, reach some sort of mechanical conclusions from this kind of thing. First of all, a sanity check. The fitted values we obtain for the stretches of these shapes do agree with what one can sort of estimate by looking at cell size measurements. There is also a sort of cell shape conundrum. Inversion starts with some region of wedge-shaped cells, which are bending the cell sheet. During this invagination, the curvature of the cell sheet increases, yet you always see the same wedge-shaped cells. So the intrinsic curvature should be constant, although the actual curvature increases. This is not something we put into the model, but we can check it from the fits, and indeed, our fitted values suggest some sort of initially constant intrinsic curvature, while the actual curvature does increase. We can also, for example, predict that this bend region expands at constant speed. But the more important conclusion is that the model has some region of intrinsic curvature that bends the cell sheet to favor this invagination of the cell sheet. But there is no idea of intrinsic curvature to drive the peeling of the anterior hemisphere in the later stages of inversion. So, and indeed, if you do a very simple test of starting with a shape like this one and propagating some sort of front of intrinsic stretches towards the pole, you can indeed complete this inversion. So while the initial stages of this process are really driven by bending, it seems that bending is not necessary for the inversion of the anterior hemisphere, which is only driven by relative stretching of different parts of the cell sheet. And so there are very different geometric modes that the cell sheet is using to do different things. And to make that idea more precise, we can actually use the variability of the cell sheet. Here's one of the shapes we saw earlier. And I'm representing, on this graph, I'm plotting the shape variation, the thickness of this area of shape variation here, against arc length of the shape. In particular, you see that there's this rather pronounced maximum of shape variation that occurs sort of over here, just beyond the bend region next door. You say, how does this variability arise? Well, in the simplest scenario, it might just be that all of the parameters describing the cell shape changes have some sort of a uniform variability, which results in this nonlinear shape variation. Actually, if you run lots of instances of this, well, you overestimate the variability at the anterior pole or the posterior pole, but mostly you don't get sort of this peak. And even if you do get sort of some sort of peak, you don't get the position of the peak right. In fact, if you plot the distribution function of the position of this maximum, the experimentally observed one is hugely unlikely to arise under this model.
I'm confused. These lines are data, the same data you had before.
Sorry, I should have said that more clearly. The blue line was the thickness of the average shape here.
I understand.
The grey lines are, I'm now taking my average shape. Sorry, I should have, you asked to write as a sentence I didn't say. I take my average fitted shape and I perturb all the parameters of the model randomly, and I then solve for all these shapes, and I average these shapes, and I get shape variations like this grey line over here, which do not reproduce.
So this is numerical calculation from the average,
Exactly.
rather than the real data.
Yes, this is a numerical calculation from the fitted average, yes. From the fitted representation of the
You
average.
could put on this graph also data.
I don't have individual, so the data is the blue line. I only have one line of data because I only have one average of the data. But I can have as many instantiations of the
Okay,
random
understand.
as I want. Yes. But in fact, I can do a very tiny modification of this game and instead allow for some additional variability of the meridional stretch in this region of the cell sheet. If I do that, and again run lots of instantiations of the perturbations.
You're doing it ad hoc.
Yes, I'm saying, let's say this was a uniform distribution. Let me take a non-uniform distribution of parameters. That's the simplest one I can come up with, simplest modification of this uniform model. And with that model, I can reproduce the average distribution I see in experiments.
If I play with this, I can fit whatever.
I don't think so. I'm looking for, there's some distribution of parameters, of variability of parameters that will have resulted in this blue curve. Of course, ideally, I would like to be able to invert the distribution of variability to get the actual distribution of the variability out of it. That I cannot do at this stage. So let me instead see if I can come up with a, as I will argue, biologically sensible simple modification of this that allows me to reproduce what I see in the data. I agree, this must be a first step. Ideally, I would like to be able to invert the distribution, but I cannot do that at the moment. I'm still sort of overestimating the variability here, but now I can actually reproduce the magnitude and the position of this peak of shape variability.
But there's some minima that don't agree.
These minima here,
Yeah.
sort of, yeah, they sort of don't agree over here, yes. But I think it's a much better representation of the global shape of this curve. Now you can think, what does it mean to have an increased variability in this particular parameter? Does that sort of fit into what I see? Well, it could either mean that there is heterogeneity of stretching, or it could mean that there's heterochrony of stretching. By heterogeneity of stretching, I mean that there are different embryos that stretch by different amounts in this region. And in fact, if I look at how much variability I need to put in over here to be able to reproduce this maximum of the shape variation, this would mean that some embryos would not stretch at all in this region, whereas others stretch a lot. And that cannot be, because we've seen earlier, for example, in these shapes, that if we don't have any stretching of this hemisphere, then I cannot invagine. There's no room for it to invaginate. So the other explanation fits much better into what we've seen. The explanation of heterochrony, that there are similar amounts of stretching in the embryos, but this stretching happens at different times relative to the main sequence. Because now this is suggesting that these different deformation modes of the intrinsic bending for the invagination and the stretching for the inversion of the anterior hemisphere also simply correspond to separate processes that have temporal leeway with respect to each other. As you said, of course, I hope this is some sort of proof of principle that we can get some information out of the variability. Ideally, we would like to be able to solve the full inverse problem and infer the full distribution of the variability. There's also a question about bifurcations in this context. In this system, we have no sort of indication there should be sort of mechanical instabilities during Volvox inversion, but in a general morphogenetic system, there's no reason why you can't have two developmental trajectories that start at the same point, one of which might cross some sort of bifurcation boundary, but as long as you get back to the same result at the end, all is fine. In the last minutes of my talk, I want to say that why some of these ideas make sense by briefly going back to the other inversion, type A inversion, where you have these four lips opening up and peeling back from the anterior pole of the shell. In particular, there are two important biological papers on this, which you might like to try to understand. This type A inversion is arrested, first of all, in a mutant called inv-A, in which you can have cell shape changes, but you can't have relative motion of cytoplasmic bridges in cells. So you can't have the same amount of splay of the cells. In the wild type, I'm not sure how much of this you can see, the lips start flipping over and eventually flip over completely. But in this mutant, the lips sort of open up, but then don't flip over. Similarly, if actomyosin-mediated contraction is inhibited chemically, invagination gets arrested. Here's the wild type, which inverts. In these inhibited embryos over here, the lips sort of start to flip over, but then inversion gets stuck. But to describe this geometrically, we need to go back to the elastic model. Now, rather than having a complete, azimuthally complete shell, we have cuts that define these lips at the anterior pole. These lips might look something like this. They have some width 2 phi, if you look at them from the top. And if you have them, you can now play with the azimuthal angle, the deformed azimuthal angle need no longer be equal to the undeformed one. Here I'm going to make a geometric simplification, which you can think of as by writing that the deformed azimuthal angle just depends linearly on the original azimuthal angle with some subscaling factor capital phi, which you can think of as taking the first term of a Taylor expansion of this azimuthal angle. The geometric gradient tensor now has additional off-diagonal terms. The intrinsic tensor is unmodified. You can play similar games, do some midline approximations to write down elastic strains. The tensors now have off-diagonal terms, and there are additional terms arising here. You can even derive the energy, which looks much more complicated. It wouldn't fit on a single slide, but the calculation is always quite straightforward, really. Now, this type A inversion has been described in great detail in the experimental literature. At the level of cell shape changes, it starts with cells being uniformly spindle-shaped, and then a region of flask-shaped cells with thin stalks forms at the phyallopore. This region then proliferates down towards the posterior pole, as shown over here, leaving behind a region of columnar-shaped cells. You can encode these observed cell shape changes into the model in much the same way as we've done before. There are various parameters that describe the width of the ellipse, the various sizes of these cells. There's the intrinsic curvature of the flask-shaped cells. And you can estimate all these parameters from previously published figures or from data in the literature. The main driving parameter that I'm going to vary in what follows is this capital theta, which describes the position of this bend region of flask-shaped cells as it is propagated towards the posterior pole. Indeed, in the simplest scenario, let's start with a large value of capital theta and reduce it down to the posterior pole, and the ellipse eventually do flip over and the shell inverts. It means that there's some points on this line where I've sort of plotted the line as a dotted line, which is where the curves suggested by this model start to self-intersect. I expect these to be sort of smoothly joined up to curves where the shell is where the ellipse are in contact with other parts of the shell. I've not solved that problem, but for example, you might see that there are other branches in this diagram, such as this one over here, on which the shell can invert without having self-intersections.
So what's the difference between these different curves?
So this is the lowest energy curve. There are other curves which you can find numerically for the beauty of it. In fact, this is only the scenario if the intrinsic curvature is large enough. Because you can imagine gluing these branches together slightly differently, gluing this branch here to this branch, and then suddenly you don't have any inversion anymore. You start over here, you stay on this branch on which it doesn't invert and the lips remain open. There are other solutions on which the shell completely inverts, but they are no longer connected by branch points to the inverted configurations. And so this does explain the inversion arrest in this mutant. If I don't have any relative motion of set basic bridges, I have less of a splay, I have a lower intrinsic curvature, and hence I don't invert and indeed get the shapes seen in the experiments. Can we use the same ideas to explain the failure of inversion in embryos in which there's no contraction? No. If there's no contraction, then the flask-shaped cells and the columnar-shaped cells, all these cells are the same size. You might ask, does this change the critical curvature that allows you, that corresponds to this transition? It doesn't change this one very much. So, lack of relative expansion cannot explain the arrest of inversion unless the system is very close to its mechanical limit. There are, however, other effects which can easily explain this. For example, the experimental paper also mentioned that if contraction is inhibited, then the width of the region of negative curvature becomes very much smaller, and indeed that hugely changes the intrinsic curvature. Why this would change, why inhibition of contraction would change the width, the number of cells that become flask-shaped is a different matter that is unresolved. And then in fact other effects can explain the same things. But I think at this stage there's one conclusion to be drawn, which is although we have seen in some detail how the mechanics of this inversion works, there's a more general sort of Evo-Devo conclusion. In that I said at the beginning of the talk that Volvox is a model organism for multicellularity because you have this prototypical transition from organisms with one cell type to organisms with many cell types, two cell types. And here we seem to see the same sort of complexity transition in development. We have processes, the development of which requires a single process of bending, and we have organisms in which we have two processes, two separately regulated processes of separate bending and separate stretching. Then, of course, there's a host of questions of evolutionary biology. How did these evolve? Did they evolve separately, or were some of these lost from some sort of an ancestral alga? Perhaps the other Volvocalis hold the answer. Thank you very much.
We have time for questions. Okay. Please, Jacques. Yes. Why don't you go
Okay,
first?
so why do you use an elastic model for all of that? Because I would expect T1 transition to exist, and at long time this system to be like a fluid rather than an elastic medium.
The fact that we have cell-cell connections, I think, inhibits inhibits of relative motion of cells. So I think that was the main reason why we would think of an elastic.
Why are you saying there is no T1 transition?
Because the cells are connected to each other by cytoplasmic bridges. So if I, for example, have these two cells over here and they're connected to each other, then this one can't move in between them because there's a connection a physical connection between these two
No, but
cells.
these connections are basically also, and certainly sufficiently long time scale, they are also fluid-like. And actually,
But,
the system is a fluid-like system.
But I can't
Like
quite
over-
see how this would change how motions of the cytoplasmic bridges could change the topology of the connectedness of the different cells.
The tissues, I mean, columnar tissue can have topological changes.
I agree, but these cells have physical connections to them. I just can't see how two cells how one cell would move in between two cells if there's actually a bar that connects these two cells.
Okay,
Yeah, we can talk about this.
we can
Yes.
make drawings.
I have two questions. One is, which of the two possible modes of inversion that you described is cheaper energetically? And my more broader question, which may be easier to answer, is why in the world did these things evolve to do this? There must be some Volvox that don't do this, or all Volvox do this?
Well, there is a genus of closely related algae called, and I will get this wrong, Astrophomini or Astrephomini, something like that, which look like Volvox. They divide in superficially similar ways, and they manage to form a spherical colony without the need for inversion. However, they don't have the same complexity as Volvox. The largest species of Astrephomini have 128 cells. I think that's all I can offer in terms of an answer to that question. Why you could sort of think of why did the need for inversion arise in the first place by saying that there's some there's some organism that perhaps developed multicellularity in some way, and as it started to divide, it somehow became slightly, there was some sort of bias to the orientation of cell division in some way, that gave it some curvature which turned out to be unfavorable. Then it somehow had to evolve a way of getting rid of that curvature. Why it just didn't get rid of the one way of division, I cannot answer, especially since some algae managed to do it. To get back to your first question, which way is cheaper? I do not know, because if you mean in terms of absolute values of energy, for example, you could say, well, what are the elastic moduli of this, which are overall constants, and which are actually we don't know what they are because they are very hard to measure. But I think there's sort of another sort of geometrical trade-off here, in the sense that when you're an organism that has to do something, you are both constrained by the local geometry and you're constrained by the global geometry. The local geometry, that's basically the rules of differential geometry. You can't do anything about it, but you can do something about it. You can do something about the global geometry. Now, somehow type A inversion manages to have a very simple inversion with this single wave of cell shape changes, but it did have to divide in such a way as to have these slips. Whereas type B inversion needs a much more complicated process of cell shape changes, but did not have to have any lips. So that might be the trade-off.
Question in the back, and then Ariston.
You did say it takes a few days for this thing.
Sorry,
How long does
1
it
hour.
hold?
An hour.
An hour, sorry, an hour. And the cells multiply, how much multiply?
and then there's no division at this stage. So
There's no
cell division happens
is it
first,
pure? Okay.
and then you have inversion.
So going back to your macroscopic picture of creating these negative curvature, you have these
Yes.
cell shapes. So it's all cell, the shape change that
Exactly.
induce these curvature. It looks like you have initiation at some.
How do they know where to do this? Is
Yeah,
that your
we used to
question?
do that. Oh, no, and beyond there, first of all, where it is, it's not at the equator, it's slightly off the equator. And then you might imagine that one way to think about the growth is that it's a propagation of the negative curvature throughout. And if that's the case, if you look at the cell images, then you can see the shapes gradually changing from where they started to about, which coincides with your notion of heterochronous.
So we cannot image single cells and their shapes in vivo.
In vivo. So how do the microbiologists?
So these are sort of fixed embryos, i.e. dead embryos, under electron microscopy. So ideally we would like to be able to image single cells in vivo, which would enable us to be able to follow the sequence of individual cell changes.
How big are they?
They are, in the stage of inversion, the diameter is about 50 to 100 micrometers.
So you could use a light sheet microscope.
So some of this data I showed, I should apologize to my collaborators for not talking about the experiments in great detail. All of this data is data from light sheet microscopy.
Light sheet microscopy.
Yes.
And it doesn't have the resolution 100 cell.
No, not for individual cells. Individual cells are order of 5 micrometers, a bit less in the other directions. You can't see that. And it also add that this is imaged by chlorophyll autofluorescence. So you're limited by the amount at which they fluoresce, which of course gives you the advantage that you can see this without having to stain the alga.
It sounds like you also had thought about where they initiated.
Yes.
That was
Well, in terms of thinking about it,
Yeah.
I think my thoughts are that it is not known. People have done some experiments which are of the sort, take one alga and smash it up. If you're lucky, you have some single cells, and you can observe them, and you will see that they undergo cell shape changes. You might also have 2 bits of, or 2 cells or 3 cells still sticking to each other, and again you will observe that one of them undergoes its polynomial cell shape changes, and the next one follows suit. So you might be tempted to argue that this suggests there's some
Propagation.
yeah, no, and maybe that the whole thing is sort of genetically programmed. I shouldn't say it's a question of gene expression, but while it seems to exclude sort of chemical signaling between cells, I don't think it can exclude sort of mechanical signaling actually, because you're smashing up an alga, so you're parting a pretty large mechanical cube.
Was the question first RSD? Yes.
So as you show in this slide, so you used time as a coordinate to average embryos between them. So
No, not time. I used a global shape, so I can say a few more words about this actually. So you can imagine us. Thank you very much. You can imagine how so having somehow different sequences of inverting embryos, and you run essentially optimization, energy minimization routine that decides which 2 points of these sequences should correspond to each other in terms of global shape. And for the global shape comparison, well, you might have to do sort of a relative stretching between shapes to allow for differences in the cell shape changes between individual embryos.
So the variability that you see is not a variability in the developmental progression, or so because I was wondering whether the larger variability at the tip that you see is not just well, folding in advance or later than the average embryo.
I think it is exactly this, but you have to say, what does it mean?
So if you take the average, let me phrase it in a different way. If you take the average embryo and you dilate time differently around that transition point that you are looking at, would you get the same variability or not as observed?
And might get a different, of course, if I start dilating time more and more, I will eventually get a different variability. But I will also get different global shapes. So that I think that there's an, also if you make any statement about an average.
So you take the average trajectory.
Yes.
And so you were looking at time t1, and you compute the variability for the based on the average trajectory between t1 minus delta t and t1 plus delta t. How would that differ from the observed variability?
It will differ in some way. I don't know in which way exactly. However, this will also change your definition of the average sequence. And so all of it boils to be able to say that we have to first make a definition of what our average sequence is, and what is the best average sequence we can come up with. This is a trade-off between making statements about global shape agreement and local shape differences.
So what I'm implying is that the variability that you see could be an error in estimating
The global shape, yes.
the average trajectory here. So you need to be careful about that.
We had an entire workshop last week. We have one more question.
So have you, with your models, or have your collaborators with experiments, wounded the Volvox in particular ways to see whether, to test your ideas, to see if the model predicts the wrong deformation that you would get with a wound?
I think these are experiments about to be done.
So not yet.
Not yet, no.
By yourself?
No.
I'm just kidding. All right, unless there's any more questions, we're out of time. So now I would please join me in thanking Pierre again.